Decartes' rule of signs is going to help us reduce the workload when dealing with the rational zeros theorem. It's going to help us by giving us the total number of positive zeros and the total number of negative zeros. As you recall, our rational zeros theorem gives us a pool of numbers from which our zeros must be present. But we don't know anything about what those zeros are. We just have a whole bunch of numbers and we just have to test randomly. What this is going to do is narrow the field a little bit. It says, well, we're going to have, let's say, 3 positive zeros and 4 negative zeros. So we know how many there are, so that's going to be able to help us limit the possibilities, and it will become more apparent when we do an example. Well, let's go over the definition. Decartes' rule of sign says, let f of x be a polynomial function with a real coefficients and terms written in descending order. 1. The number of positive zeros of f is either equal to the number of variations of sign of f of x, or less than that number by an even integer. So what this is saying that the total number of positive zeros for a function of x is equal to the number of changes of sign, or less than that by an even integer. An even integer is 2, 4, 6. So it's going to be less than by basically a series of 2's. So don't let that confuse you. The number of negative zeros of f is either equal to the number of variations of sign of f of minus x, or less than that by an even integer. And then there is a note that says, when using Descartes' rule, a zero multiplicity m should be counted as m zeros. And what that means, I might as well go over this first since we just talked about this last. What that means is, say we have some function x plus 2 times x plus 2. So here we have something that has 2 of the same zeros, minus 2. And what that's saying is that these zeros should be counted separately. This is 2 zeros, not 1, even though it's the same one. But let's go back up here, where we're talking about variations of sign. The number of positive zeros of f of x is either equal to the number of variations of sign, so the number of changes in sign, or that number less than some even integer. So I'm just going to make up some random equation, and we're going to talk about Descartes' rule of sign. So let's say I have some equation x to the 6th minus x to the 5th minus x to the 4th plus x to the 3rd minus x squared plus x to the 1st minus some constant. Or we can just change it to a number, it's minus 1. And this is f of x is equal to. So let's use Descartes' rule on this polynomial. So if we want to find the positive zeros, we have to look at the changes in sign. According to this rule, it says that the number of positive zeros is equal to the changes in sign of the function f of x, or some number that is less than an even integer. So let's start here. X to the 6th is a positive coefficient. This is a minus, this is a minus, this is a positive, this is a minus, this is a positive, this is a minus. So let's look for variation in signs. We start out as a positive, and then we change to a minus. So this is one variation. Then we go from a minus to a minus, so it's the same, so there's no variation in sign. Then this goes from minus to positive, so here's a second variation in sign. Then we go from a positive to a minus. So this is a third variation. A minus to a positive, a fourth variation, and then a positive to a minus, a fifth variation. So according to Descartes' rule, there are going to be 5 zeros because there are 5 variations of sign, or less than that by an even integer. An even integer is 2, 4, 6. So it's going to be less than just basically a series of 2. So if we subtract 2, then there's 3. And if we subtract 4 or another 2, then there's 1. So the number of positive zeros is going to be equal to 5 or 3 or 1. Not all of them. It's either going to be 5, 3, or 1. We don't know which. And for the negative zeros, we have to put in minus x. So we put in minus x in for all of these. So minus x to the 6th, minus x to the 5th, minus x to the 4th, plus minus x to the 3rd, minus x squared, plus minus x, minus 1. So this is an even power, so this is going to be positive. This is a odd power, or an odd function, an odd power, so it's going to be still negative, so this is going to become positive. This is an even one, so x to the minus 4th. This is an odd one. This is an even one, so it's not going to change. This is an odd. So now let's look at the variations in sign. So positive, positive, minus, 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 minus. So we have a positive. We start with a positive, and then we go to the next one, and this is still positive, so there's no change in sign. Now we go from a positive to a minus. So here's one variation. And we go from a minus to a minus, so there's no change, minus to a minus, no change, minus to a minus, no change, minus to a minus, no change. So for our negative zeros, there is only a possibility of one negative zero. And even though it says or less than that number by an even integer, if we take away an even integer, the smallest even integer being 2, then we're going to get a negative number, and we're not going to have negative quantities of zeros. So that's not possible. It doesn't even make any sense. So there's only a possibility of one negative zero, which is extremely helpful to us, because if we find it, so if we come up with our, let's just say we do P over Q and then we get a pool of numbers. If we find this negative zero, so for positive zeros, it's 5 or 3 or 1. For negative zeros, there's only 1, and that's it. That's the only way it can be. There must be a negative 0, and there's only 1. So if we get a pool of numbers, we usually get plus and minus some number A, plus and minus some number B, plus and minus number C. If we find the negative 0, then we can forget about the negative numbers, because there's only 1. So that helps us reduce our workload. Where in the past, we didn't know that there was only one negative number. So even if say we found the negative number right away, the negative 0 right away, then we would still have to check all the other ones, because we'd have no idea that there was only 1. So that's a way that it can reduce the workload. So let's do an actual example. I have f of x is equal to x to the 4th minus x cubed minus x squared minus x and minus 2. And I want to know, I want to find out the zeros of this function. So first what we can do is use Decartes' rule of signs. So we have f of x. This is positive, this is minus, this is minus, this is minus, this is minus. So we can see that there's one variation here. So one variation, and then it's the same the rest of the way. So there's only one variation for f of x. So the number of positive zeros is equal to 1. Because we can't subtract an even integer from 1. So there's only one possible amount of positive zeros, and that is 1. Now let's put in f of minus x. I picked the wrong color. It's f of, minus x. This is equal to negative x to the fourth minus x cubed minus x squared minus x minus 2. And in fact, we don't really even have to do this, because we know this is x to the fourth, and therefore there can be a maximum possibility of 4 zeros. And if there's only a maximum possibility of 1 zero for the positive ones, then there must be a maximum of 3 for the negative ones. But never mind that. I mean, if you don't get that, then just do it the long way. So this is going to be equal to x to the fourth. Minus x times minus x times minus x is minus x still, so this can change to a positive x cubed. This is still going to be a minus x squared because the minus sign is cancelled out. A minus minus x, that's positive x, and minus 2. So this is a plus, this is a plus, this is a minus, this is a plus, this is a minus. So plus to plus, there's no change. Now plus to minus, that is one variation. Minus to plus, that is two variations. And plus to minus, that is a third variation. So we have a possibility for negative zeros, possibility of 3, or we subtract even integers. That's what the one I was looking for. Even integers, so we subtract 2, and we have a possibility of 1 as well. So there are either 3 or 1 negative zeros. Now we should start doing synthetic division. So let's start with, we'll just start doing the positive ones. So let's rewrite our equation. F of x is equal to x to the fourth minus x cubed minus x squared minus x minus 2. So the first thing we need to do now, actually let's write over here what our zero possibilities are. So positive zeros are 1, negative zeros 3 or 1. So let's find our p over q. P, remember, is the coefficient of the constant, and q is the coefficient of the leading term. And our constant factors are equal to plus and minus 1 and plus and minus 2, and our leading coefficient factors are just plus and minus 1. So we have plus and minus 1, plus and minus 2, and we divide them by plus and minus 1, and then we're going to get possible zeros of plus and minus 1 and plus and minus 2. So already we can eliminate quite a few possibilities. We have 4 possible zeros, plus and minus 1 and plus and minus 2. These are the only zeros that are possible. We have 1 positive 0, and we can have 3 or 1 negative zeros. But right here we can just look over, we only have 2 negative zeros. We have minus 1 and minus 2. So we can already cross out 3 as a possibility. So we know we have 1 0 that is positive, 1 0 that is negative. And what's really convenient about this, because there's only 2, if we pick one and find out that it's not that is not the 0, then there's only one possibility, and that's the other one. So that is significantly less work. When we were doing these problems before, we had no idea how many zeros there were. So we would have had to solve for all of them. But now we've just eliminated half the work, because we know there's one positive 0 and one minus 0 now. And if it's not one, it's the other. So let's do synthetic division. We'll try 1 first. So we have 1, minus 1, minus 1, minus 1, and minus 2, I believe. Let me scroll up and check. Yeah. Don't want to do a whole bunch of synthetic division and then have it be wrong. So 1 times 1 is 1. 1 minus 1, 0. Bring the 0 up here. Minus 1, minus 1, minus 1, minus 1. This is minus 2. Minus 2 times 1 is minus 2, and this is minus 4. And this is not a 0. So 1 is not it. So therefore it has to be 2. Because we only have one positive 0. And positive 2 is the only other option we have. But let me just do the synthetic division anyways, just to show that this is indeed true. So we have 1, minus 1, minus 1, minus 1, and minus 2. Bring that down, multiply by 2, we get 1, multiply that by 2, we get 1, multiply that by 2, we get 1, multiply that to 2, we get 2, and then we get 0. So we can say that x minus 2 is a factor. But we already knew that from before. This step was completely unnecessary because of Decartes' rule of signs. We know there is one positive 0 out of 2 zeros. So if it's not 1, it has to be the other. We did 1, it wasn't 1, so therefore it must be 2. And I just did this just to show. So we're left with, so when we pull out x minus 2, we're left with x cubed plus x squared plus x to the first plus 1. How nice. And now we need to check for our negatives, and we found out that it was either 3 or 1, but since we only have minus 1 and minus 2 as options for the negative zeros, we know it can't possibly be 3 because we don't have 3 negative numbers in our pool. So let's try minus 1. So this will be an easy one. Bring down the 1 times by minus 1. This is minus 1. This is 0. 0, 1, minus 1, 0. So this is a factor. And we're done, because it has no more zeros. No more rational zeros anyways. So we're left with x minus 2, x plus 1, x squared plus 1. And we can see why that there are no more zeros, because there is no number that is a real number anyways that we can put in here to get 0. I mean, what squared plus 1 is going to be equal to 0? There are going to be imaginary solutions for this, but we're not going to start talking about that until we go over the fundamental theorem of algebra. And in fact, that's why we subtract even integers. Because there are a pair of solutions for this. It can be I or minus I. So don't worry about that. We're gonna learn about that when we start talking about the fundamental theorem of algebra and the complex conjugates. I think it's called the complex conjugates theorem. But either way, we're gonna have, every time there is a complex number, they come in pairs that can be solutions. So that's why we have to subtract even integers. But that's Descartes' rule of sign for you. It's just something that helps us reduce our workload when dealing with the rational zeros test. Because you have to remember that when people were doing this stuff back a few hundred years ago, they didn't have computers, they didn't have calculators, so every equation they had to do out by hand. And if they had some equation where they had large coefficients for the constant and the leading coefficient, then they would have a huge pool of numbers, and any work they could take out, then it was a huge help to them. So this is why these theories are so developed. And we're going to learn about the bounds too, and that's also going to help us reduce our load as well.